every AI system you use in 2026. From ChatGPT to Midjourney to your phone's Face Unlock, runs on neural networks that learned patterns from data. But how does a mathematical system actually learn? Let's break down the real mechanisms. Neural networks aren't programmed with rules. They're trained through exposure to millions of examples, adjusting internal parameters until they can recognize patterns humans never explicitly coded. Understanding this process is the key to understanding modern AI. First, what does learning a pattern actually mean? When a neural network learns to recognize a cat, it's not memorizing cat images. It's discovering mathematical relationships between pixel values that correlate with catness. A network trained on 10,000 cat photos builds internal representations of edges, textures, whiskers, and ear shapes, statistical patterns that distinguish cats from other objects. This happens through numerical optimization, not symbolic reasoning. The basic building block is the artificial neuron. Each neuron receives inputs, multiplies them by weights, adds a bias term, and passes the result through an activation function. A single neuron in an image classifier might activate strongly when it detects a vertical edge at a specific location. Modern networks like GPT-4 contain hundreds of billions of these neurons arranged in layers, each learning increasingly abstract patterns. Learning starts with forward propagation. Input data flows through the network layer by layer, with each neuron performing its calculation. For an image classifier, raw pixels enter the first layer. Intermediate layers detect shapes and textures, and the final layer outputs probabilities for each category. Initially, with random weights, the network's predictions are pure noise. Maybe 10% accuracy on a task where random guessing gives 10%. The loss function measures how wrong the network is. For classification, cross-entropy loss compares the network's predicted probabilities to the true labels. If the network predicts 5% probability for cat when the image is actually a cat, the loss is high. If it predicts 95%, the loss is low. Every training example produces a loss value, and the goal is to minimize average loss across all examples. Backpropagation is where the magic happens. This algorithm calculates exactly how much each weight contributed to the error. Using calculus, specifically the chain rule, backpropagation traces the loss backward through the network, computing gradients that show whether increasing or decreasing each weight would reduce the loss. This is pure mathematics. Partial derivatives flowing backward through millions of parameters. Gradient descent uses those gradients to update weights. The gradient tells you the direction of steepest increase in loss, so you step in the opposite direction. The learning rate controls step size. Too large and you overshoot the minimum. Too small and training takes forever. Modern optimizers like Atom adapt the learning rate for each parameter, converging faster than simple gradient descent. A typical training run performs millions of these updates. Weight updates happen in batches. Instead of updating after each example, networks process mini batches of 32, 64, or 256 examples, averaging their gradients. This smooths out noise and leverages parallel processing on GPUs. Training GPT-4 involved processing trillions of tokens in batches, with each batch slightly improving the network's ability to predict the next word. The cumulative effect of billions of updates transforms random noise into coherent intelligence. Generalization is the ultimate test. A network that memorizes training data is useless. It must recognize patterns in new data it's never seen. Regularization techniques like dropout randomly disable neurons during training, forcing the network to learn robust patterns rather than memorizing specifics. The difference between 90% training accuracy and 70% test accuracy reveals overfitting. In 2026, the best models achieve near-human generalization through architectural innovations and massive, diverse datasets. Architecture determines what patterns can be learned. Convolutional layers in image models exploit spatial locality. Nearby pixels are related. Transformer attention mechanisms in language models allow every word to influence every other word, capturing long-range dependencies. Residual connections let gradients flow through hundreds of layers without vanishing. These architectural choices encode inductive biases about the structure of the problem. Data quality trumps quantity. A network trained on 10,000 carefully labeled, diverse images often outperforms one trained on 100,000 noisy, biased images. Modern training pipelines in 2026 use synthetic data augmentation, active learning to find informative examples, and careful filtering to remove mislabeled data. The pattern is clear. Garbage in, garbage out, but gold in, intelligence out. Training versus inference is a critical distinction. Training requires massive compute, weeks on GPU clusters, millions of dollars in cloud costs for frontier models. Inference, running the trained network on new inputs, is comparatively cheap. Your phone runs billion parameter models in real time because inference requires only forward propagation, no back propagation or wait updates. This asymmetry drives the business model of AI in 2026. So neural networks learn patterns through iterative optimization. Random weights become useful representations through millions of gradient descent steps, each slightly reducing prediction error. Backpropagation computes the necessary adjustments. Architectures encode structural priors, and generalization emerges from the right combination of data, regularization, and scale. This process, not magic, just calculus and statistics at massive scale, powers every AI breakthrough you see. If you want to understand AI deeply, subscribe for weekly explainers that cut through hype and show you how the technology actually works. Hit the bell so you don't miss the next one.